All right, this video is going to talk about curve sketching and how we can use the derivative and second derivative, as well as everything you've learned about graphs to sketch a curve without the calculator. Now, we might want to use a calculator to just confirm our answers. You're able to do that, but we really want to be able to do this calculator inactive. There are some steps here that you can follow. I want to highlight just a couple things. The first is we won't really evaluate limits on this. We'll think about it conceptually. We'll think about end behavior. We'll use some of the horizontal asymptote rules. We will look at one that has a slant asymptote or an oblique asymptote. And then we will look at vertical asymptotes just like we would before, looking again at derivatives and second derivatives like we've been doing. So that's kind of in a nutshell the steps that we will take. And I want to walk you through some examples. So you have in the past been able to graph polynomials and look at their graphs just by using their zeros, but you might not have actually known where maximums and minimums and those types of things are. So something we might have done in a pre-calc class is when you look at this function, you can say, okay, well, f of 0 would be -1 squared times 2 is 2, and then I could find the zeros of this function as x equals 1 with a multiplicity of 2 because of that squared, and x equals -2 multiplicity of 1. And using those data points, you could have found a general shape of our curve. Now, end behavior here, this is going to be an x cubed function. So end behavior is here and here. And I'm going to go through at -2, bounce, and go back up. But that's kind of the general sketch of the curve that you could have done in a college algebra or pre-calc class. We want to take this further. So there's no vertical asymptotes because it's a polynomial. I don't have to worry about domain restrictions or anything like that. I need to find the derivative and second derivative. I'm not going to use product rule to do this. I'm going to go ahead and expand this out. Just to save time, I did this separately, and you get x cubed minus 3x plus 2, if you do that full expansion. All right, so let's look at the first derivative of that. That's going to be 3x squared minus 3. And I want to find the zeros of that to find the critical points. I'm going to factor out a 3. I'm left with x squared minus 1. And I get 3 times x minus 1, x plus 1. And so it looks like I have critical points at plus or minus 1. Let's go ahead and test this on a number line. All right, if I plug numbers into f prime, numbers that are smaller than -1, let's see what ends up happening here. So if I plug in 3 is always going to be 3, but if I plug in like -10, I'd get a negative and a negative, and a negative times a negative make this positive, so f must be increasing. If I plug in 0, I end up getting a negative, so f must be, just move this down, I'm going to erase this part right here. Oops. There we go. All right, f must be decreasing. And then if I have another number up here, like 10, whatever, I plug that in, I end up getting positives increasing. Now you can look back at our graph that we did here and be like, oh yeah, that makes sense. So I must have a max at x equals -1. And a min at 1. Now mine doesn't really have that max at 1, or at -1, excuse me. So probably my graph really should have like a maximum and then come back down, right? So I might be able to fix that a little bit. I can also find f double prime. That's going to be 6x. And if I look at 0, it is my only 0. F double prime and then f. So for values where x is less than 0, I get negatives. So f must be concave down. Well, that makes sense. Okay, and then numbers where x is positive, I end up getting positives for my f double prime, so f must be concave up. So that makes sense. So 0 must also be my point of inflection. So this is a better graph probably. And that's basically what we're going to be doing. It's just like making better graphs of the graphs that we learned in college algebra and pre-cal with some extensions as well. All right, let's go ahead and look at sketching a rational function. So the first thing I want to look at is any domain restrictions. And I'm noticing that the denominator equals 0 at x equals plus or minus 1. And I don't have any holes in the top, or any factors in the top, I should say, that cancel with the denominator. So there's not going to be any holes in this one. So these are both vertical asymptotes. Let's also look at maybe f of 0 is going to be 0 over 1, so that's 0. And then also my zeros of my function, well, that's only when x squared equals 0, so that's it, 0. So those are some things that I know. Oh, we could also look at horizontal asymptotes just by looking at our behavior of the top and the bottom. Now these behave at the same rate as you go to infinity. I have 1 over negative 1. So I'm going to have a horizontal asymptote of y equals negative 1. All right, let's put some of that together here on the graph. So vertical asymptotes at negative 1 and positive 1, and a horizontal asymptote at y equals negative 1. All right, so now we have to find increasing, decreasing intervals by taking the derivative, find some maximums and minimums, and just find some values that are going to be of interest for us. So let's go ahead and find f prime. And I need to use quotient rule here, so I'm going to have low d high minus high d low all over low squared. All right, if I take this and distribute out in the numerator, I get 2x minus 2x cubed. And then over here, I end up getting plus 2x cubed. So these are like terms, they end up canceling, and I get 2x over 1 minus x squared. Now remember, critical points are where my derivative is 0 or undefined. So undefined, I'm still going to use x equals plus or minus 1 in my number line that I do here, but then also for equal to 0, that's just the top, so x equals 0. So let's go ahead and put those in. So negative 1, 0, and 1, f prime, and f. And if I plug in values smaller than negative 1, let's go ahead and see what happens. Well, the bottom is always positive, right? Because I'm taking something and squaring it. And then the top is going to be the same sign as whatever x you're plugging in. So negative over positive, f is always negative here. So f must be decreasing and then decreasing. And then same thing, denominator is always positive. So if x is positive, then the numerator is positive and the whole thing is positive. So it looks like I have a relative minimum here somewhere on my interval between my axes, or between my vertical asymptotes. And then something's kind of funky happening here. So we'll have to look at what might be going on here in a second. Okay, I'm going to clear this area to give us room to find f double prime. All right, so f double prime is again going to be low d high minus high d low. All right, I have to do some chain here. So 2 1 minus x squared to the power of 1, and then times negative 2x for the derivative of the inside, all over low squared. So that's going to be to the 4th power. I can factor out one of these 1 minus x squareds from both of the terms, and I'm left with 1 minus x squared times 2. And then it looks like it's going to be plus 8x squared. All over this to the 4th. This cancels with one of these, so I have this cubed. And then with some simplification and combining like terms here, we're going to get 6x squared plus 2 all over this right here. Come on, there we go. Okay, so again, on my f double prime here, I'm going to have some points of interest here at plus and minus 1. But then I also want to look at this top part right here. So notice on this top part here, I actually don't have any zeros because 6x squared plus 2 is something that's always positive. So really the only term, like places I need to look for changes in concavity is when the denominator is undefined. Like I just want to check and make sure in each one of my pieces on my graph that I know what the concavity is going to be in those places. So let me, again, I need a little bit more room here. So let me kind of simplify this and rewrite it. All right, so f double prime, I'm looking just at those vertical asymptotes to try to figure out what's going on so I can sketch this graph. All right, if I plug in values like negative 10, we said the numerator is always positive. When I have 1 minus 100, I'm going to have a negative, and then I'm going to cube it, so I'm going to get a negative there. So positive over a negative gives me a negative, concave down. If I plug in something like 0, I get a positive, concave up. And then same thing happens over here where if I plug in big numbers and then square them and 1 minus that big number, cube it, negative. All right, so let's use all of this together to sketch our graph. Between negative infinity and negative 1, I need a function that is always decreasing and always concave down. So that's going to have to look something like this, and I'm going to hug those asymptotes, right? Bam. All right, between my two vertical asymptotes, I need to have a minimum at 0, and I know 0, 0 is on my graph. And I need to be concave up the entire time. So it must look something like this. And then in the part that is bigger than x equals 1, I need something that is concave down but increasing the whole time. So concave down and increasing would look like this. And so that's our graph. And you can check that on Desmos and see that that is definitely the graph of that function. Pretty stinking close.